Hello, everyone. Welcome to this week's LLM Systems Seminar. It's my pleasure to have Zhuang Wang here to give us a guest lecture. Zhuang is a research scientist at AWS AI right now.
The title actually is applied scientist.
Okay. He is an applied scientist at AWS AI, though no, he did research. He received his PhD from Rice University, and he has actually had this amazing short PhD, because I remember when I heard you graduated, it's only about 4 years, which is pretty unique for systems people. And also his research interests focus on efficient training and also serving systems for large language model systems. And today you're going to tell us about Gemini, this fault tolerance system for training. And what's yours?
Thank you. Thank you for the introduction. And today I'm going to introduce Gemini, which is, I think it's the first paper talking about in-memory checkpoints to enable fast video recovery in the pre-training of large language models. Yeah, this paper actually has been 2 years. And the slides was made 2 years ago. So some data, some results may outdated, but the trends is still similar. For the trends now, when we started this project, the large language models that's not that popular. Many papers are still talking about BERT or GPT-1 or something like that. But we observed some trends. The large language models are gonna be very popular, will be the future. So we actually have observed 3 very unique characteristics of large language models for training. The first one is we can see the models become larger and larger. The table was made 2 years ago, so it starts from 2020 to 2023, but trends is still there. In 5 years ago, in 2020, the largest model in the community is named Turing NLG, and the number of parameters is around 70 B. So at that time, it's super large, but now it becomes a small model. And then after 3 years, when OpenAI released the GPT-4, the number of parameters becomes 1.7 trillion, which is around 100 times the increase. This is crazy. And another trend is in order to train such a large language models, we need to get more and more GPUs or TPUs or accelerators, given the kind of accelerators involved. Say for Turing NLG, only 256 V100 GPUs were used, but as reported by Google in 2022, they uses more than 6,000 TPU V4 for the training of a Palm. Another trend is that the training time also becomes larger and larger. For the 2021, the training time is around 2 months to train a large model. But in 2022, Palm takes 2 months to finish the training, and the GPT-4 it takes around almost a half of the year. And now I think for the trend is the MOE becomes the standard for large language models. It has even more and more parameters. So though we don't have any data for the training time, but I guess the training time even becomes much longer today. And so consider the training system as a distributed, huge, extremely huge, large distributed system, and the running time is also extended. It will last a couple of months or even half of a year. So the many types of failures may show up. It's inevitable, and different types of failures are very frequent. We may experience software failures. Library, we are using different libraries like the NICO, the communication library, or the framework. And no matter you are using Megatron, Torch, whatever, so you may experience some bugs in the frameworks. And another thing is during the training, you need to save, not just save. First, pull some training data from the remote storage system And you also need to save the checkpoints and push them to the remote storage system. So the remote storage can also get down. And another thing is the hardware failure is very common. Like the GPU can crash at any time because we have thousands or even tens of thousands GPU involved in the training. And the hardware in the network, such as the link, the switch, can also fail at any time. And as reported in the OPT 175B paper, which is open sourced Llama model from Meta, they have a blog, they have a paper reports the training and also mention the failures. Like in over the course of 2 months for the training, it suffers more than 100 failures. This is a lot. And they also reported like the total wasted GPU time is around 200,000 hours. This is huge, and it's a very practical and a fundamental problem for the pre-training of large language models. And a common way and a widely used way to recover training from failures is checkpoint. So I can briefly introduce how checkpoint works. So the training system will need to particularly checkpoint the model states, and then you will upload because the CPU memory or the GPU memory is very small. It cannot save all the checkpoints. So the training system typically will send the checkpoints to a remote storage system. And then in case of unexpected failure, the system can retrieve the checkpoints and then restore the training from the latest checkpoint instead of like get started from the very beginning. And after that, because we can see there's some wasted time, we have to redo some computation, and we call the time period between the failure time point and the latest checkpoint as a wasted time. So the goal of the checkpoint, one of the goal of the checkpoint is to minimize the wasted time. So obviously, a higher checkpoint frequency can reduce the wasted time. But unfortunately, the practical checkpoint frequency in pre-training of large language models is limited because when we need to push the checkpoints to the remote storage, it can take a very long time. Let's take a Palmer's example. The number of parameters is over 500 billion, and so the checkpoint size is 6.5 terabytes because we need to save the weights, save the optimize the states and everything. So suppose the network connecting the GPU instances and the remote storage system is 20 gigabit per second. So we can do a simple math. It will take more than 40 minutes to upload each checkpoint. And the checkpoint frequency actually is limited by the checkpoint time because we cannot start a new checkpoint until we finish the previous one. Otherwise, they will have some contentions in the network. The network becomes the bottleneck. Now, I can give you a more concrete example to showcase how it works, why the checkpoint is a big issue in the pre-training. Suppose we save the checkpoints for every 100 iterations. Say at iteration 100, we save the first checkpoint, and in iteration 200, we save the second checkpoint, and then the third one. But unfortunately, we have an unexpected failure. So at iteration 310, and then it interrupt the third checkpoint. In this case, the third checkpoint is not completed. So we have to retrieve the previous one, the checkpoint 2, failure recovery. And then it will also take a very long time to pull the checkpoint 2 from the remote storage. So and then the training can get started to can be resumed from iteration 200. So we can see the wasted time is very long. And even we can, like I say, so when we are doing that work, like people are not choosing the extreme high checkpoint frequency, because for Bloom, I'm not sure if you're familiar with this open source project, which is used to train open source large language models. Like a couple of months is a very reasonable checkpoint frequency. But even with the highest checkpoint frequency, which means we can saturate the network, the wasted time is still non-negligible, non-trivial. We can see here. Like let's take Palm as example. Suppose the network bandwidth is 20 gigabit per second. So based on the example I showed to you, the average wasted time for every trainer is over 100 minutes. And because we have thousands, even tens of thousands GPUs involved in the training, and we can suffer hundreds of failures during the extended training time. So significant GPU resources has been wasted to handle failure recovery. So in order to address this problem, we propose Gemini. The key idea, so as we discussed the previous solution, just use the remote storage to save the checkpoints. And our solution is to save the model states to the CPU memory for failure recovery. And it's feasible because of several couple of reasons. The first one is the CPU memory is much larger than GPU memory. So the table here lists some GPU instances in different GPU clouds, GPU clouds. So you can see the CPU memory each machine is typically like 4 times higher than the GPU memory capacity. It means because the checkpoints are generated on the GPU side, it means the CPU memory size is big enough to store checkpoints, even multiple checkpoints. And the second reason we are choosing this design is with checkpointing to the CPU memory can enable a much higher frequency because the network connecting the GPU instances and the remote storage system is pretty low. Like in S3 in the AWS, the bandwidth is just like a couple of gigabytes or like gigabits, sorry, not bytes. So even like tens of gigabits is super slow because the S3 is not designed for large language model training. But when we checkpoint when we checkpoint the model states to the CPU memory, we can actually utilize the network bandwidth connecting the GPU machines, which is much faster. For example, when we're doing this project, we are using P4D instance in AWS, and the network bandwidth is 400 gigabit per second. And now in a newer version of GPU instances like P5, P5E, the network bandwidth is over 3,000 gigabit per second. It's much faster than the bandwidth connecting the remote storage. And the last one is for the design, someone may concern, like say, so though the CPU memory is big enough to store a couple of checkpoints, but we cannot save all of them in the CPU memory. That's true. So we analyze the different purpose of saving checkpoints, and we can divide the purpose into 2 categories. And the first one is for failure recovery, which will require high frequent checkpoints, but we actually only need the latest one. And another kind is for debugging and for accuracy evaluation. So in this case, we will need a history of the checkpoints, but it can accept lower frequent checkpoints. Based on this observation, Gemini choose to store the checkpoints for failure recovery on the CPU side, on the CPU memory. And we are still using the remote storage system and for the other category. This is why we give the system a name Gemini, but we didn't expect the Google's large language models also named Gemini. It causes another of a confusion at that time. And let me introduce the architecture of Gemini. It has two modules. The first one is for checkpoint creation. It's more like the data plane of the system. So the GPU machines can save the checkpoint, the model states, to the CPU memory in its own CPU memory or the CPU memory on a remote GPU instance. And at the same time, the machines can also push the checkpoint to the remote storage system. And we also have a control plane. It's named failure recovery module. We use a distributed key value store here, and which is mainly used to monitor the health status of the machines. And one of the machines is selected as the root agent, which can interact with the cloud operators. In case some machines get down, become faulty, have some problems, this root agent can interact with the cloud operator to kick out these faulty machines and get some new machines in the training system. Because we are considering in realistic training workloads, we are considering synchronized training, which means the total number of machines should keep constant in the entire training cycle. So not like the training with small instance, they can change the number of machines or GPUs at the runtime. But no, actually, at that time, like 2 years ago, like even now, the standard is still using the same number of GPUs, same number of machines for the entire training cycle. This design seems simple but efficient, but incurs two challenges. The first one is unlike data stored in the remote storage system, data saved in the CPU memory can get lost when the machine is down. And our solution is using the checkpoint redundancy. Like we can save multiple replicas of the checkpoints in the CPU memory. Actually, now we are not just talking about CPU memory in one machine. We are talking about the CPU memory in all the machines involved in the training. So it becomes actually a memory system. And for example, suppose we have 3 machines here, and the checkpoint generated on machine 1 can be like saved in the local CPU memory in itself. And at the same time, it can be saved in machine 2 and machine 3. So in case of failure, when machine 1 is down, we still have machine 2 and machine 3, which will have some available checkpoints for machine 1. But another design choice is the erasure coding, which can encode the data and then break it into multiple pieces. A subset of the data pieces can recover the entire data to tolerate failures. But we don't choose it because of 2 reasons. The first reason is the computation cost is very expensive, because the checkpoint size on each machine could be hundreds of gigabytes, because the model is extremely large, and the computation time for the encoding for this large amount of data, no matter we are using CPU or GPU, could be like longer than the iteration time. So it's not a good idea to spend such long time for encoding. And the other reason is erasure coding can save some memory footprint, but actually based on our observation, Gemini use memory for checkpoints, but it will take 20% of the memory capacity is enough. So CPU memory in this case is not a bottleneck. So we are still choosing the simple way, just replicate the checkpoints across machines. But we know that it's in practice we may suffer concurrent failures, which means multiple GPU machines can fill at the same time. And in this case, so suppose we have three checkpoints here, like checkpoint replicas here, but all the machines get down. All these machines get down. It means we don't have any available checkpoints from the CPU side. So we have to retrieve the checkpoint from the remote storage. It will take a very long time to resume the training. And then it comes to the first research problem, mathematical problem in this paper. What's the optimal checkpoint placement to maximize the probability of failure recovery from checkpoints that has been saved in the CPU memory? And our solution is named the group placement strategy. Suppose we have M machines in the training system, and we need M checkpoint replicas. So M here could be 2, like a 3, 4, or whatever. But like later, so because Gemini is one thing I need to mention is like because Gemini is the first memory checkpoint paper. We have many follow-up works. Some paper states when they criticize our work, they state Gemini can only support like 2 checkpoint replicas. It's not true. It's very flexible. We can support any number of checkpoint replicas. And for the group placement strategy, we have 2 steps. The first step is all the machines, all the M machines will be divided into the disjoint groups, and then each group will have M machines. The second step is the machine will back up the checkpoint replica for all the other machines in the same group. So I can use a more concrete example to showcase. Suppose we have 6 machines and we need 2 checkpoint replicas. In this case, we will divide the machines into 3 groups, and each group have 2 machines. And then in group 1, machine 1 and machine 2 will back up the checkpoints for each other. So we can see the machine 1 and machine 2 will save two different checkpoints. One is for machine 1, the other is for machine 2. Similarly, machine 3 and machine 4 will back up the checkpoints for each other, and so on and so forth. It's simple, but this group placement strategy, we can prove that this strategy is optimal in terms of the probability for failure recovery. And another very interesting observation is we observe, we do a projection, and we found 2 checkpoint replicas can already handle most of the failure cases. I think this is why the confusion comes from. This projection, we just assume the machine failure is just a random and uniformly distributed across all the machines in the system. And when we have 2 checkpoint replicas, and we assume 2 machines can fail at the same time. So when the number of machines is 16, the recovery probability is 93%. And even we assume 3 machines can fail at the same time with 2 checkpoint replicas, the probability is still 80%. And we can see at the trends, we can see with more and more machines involved in the training system, the probability becomes higher and higher. So typically the number of machines in a large scale training system could be hundreds or even thousands. It means the probability could be over 99% with only 2 checkpoint replicas. Traffic can interfere. Sorry. The checkpoint traffic can interfere with the training traffic, which, as I mentioned, because and let me follow the flow. Previously, when we only save the checkpoint to the remote storage, we have different networks for the training and for the remote storage system. So actually they're separate. So in this case, the checkpoint traffic and the training traffic are using different network, and they don't have any interference. But if we checkpoint the model space to CPU memory, it means the checkpoint traffic has to share the same network as the training traffic. So without a very good scheduling, it may harm the training throughput. But nowadays we don't have these issues because when data parallelism is used, we don't need to transfer the checkpoints to another machine. But still, I talk about the challenges discussed in the paper. Thanks to the extremely high network in the training system, we observe the network is not always fully utilized. We can always find some idle time spans in the network. So in this way, it means if we can have a very good traffic scheduling algorithm, we can interleave the checkpoint traffic with the training traffic. And the best scenario is the training throughput keeps the same as the case without any checkpoint traffic. But one issue here, because when we do the communication, it will involve some GPU memory consumption because we need to have some buffers for the communication. And because the GPU memory is mainly used for training, and we have very limited GPU, free GPU memory for the checkpoint traffic. And when the idle time span is small, we can support a small checkpoint message, then it will consume very small GPU memory. But if the idle time span is large, it can support a large checkpoint traffic message, then it will consume a large GPU memory. Then it may cause out of memory issues. Then the question is how to minimize extra GPU memory consumption. The idea is still simple but efficient. We are choosing the checkpoint partition and the pipelining. The key idea is we only need to reserve a small GPU buffer at the receiver side, and then we just further partition the buffer to multiple sub buffers. Then, because we have multiple sub buffers, and we then partition the checkpoint also to small chunks with the same size as these sub buffers. In this way, we can pipeline the checkpoint communication. For example, on the receiver side, the GPU will partition this buffer, the receiver buffer, into two sub buffers, and then the checkpoint traffic message can send to the first sub buffer and then the second one, and then it can be reused then to the first buffer first, and then the second buffer, the first buffer, and so on and so forth. So because this GPU sub buffers can be reused, in our evaluation we found a very small GPU buffers like 128 megabytes can already to support tens of or even hundreds of checkpoint size. And then let's talk about the training resume from failures. In case of software failures, because the checkpoints are already available local in the CPU memory, so we don't need to do anything but to load the checkpoints from CPU memory to GPU memory. Because in Gemini, each machine will need each checkpoint will first to be saved in its own machine first, and then transfer to the other machine. It means each machine, the CPU host in the host memory, each machine can always have its own checkpoint. So in case of software failure, we can directly load the checkpoint from CPU from a host to HBM. Then the retrieval time is negligible because the CPU, the checkpoint is already the host. And in case of hardware failures, the checkpoints are still available. So some machines are down, but we still have available checkpoints on other machines. In this example, suppose machine 2 and machine 4 are broken, then the first step is we will requested 2 new machines to replace these 2 faulty machines, and then we reuse the rank ID. Say we give the 2 prime and 4 prime, and then machine 2 prime will retrieve the checkpoints from machine 1 because machine 1 has a checkpoint for machine 2. Then machine 4 prime also retrieve the checkpoint from machine 3. And then after that, we can resume the training. Still, we don't need to get to the remote storage for the training recovery. It's still very fast. But let's consider an extreme case. All the machines are down. So we don't have any available checkpoint for one machine. In this extreme case, it's very rare, but in this extreme case, Gemini still need to roll back to the traditional remote storage solution and to retrieve the checkpoints. But the probability of this case, I think, is less than 1%. Okay, then last section is about the evaluation. So at that time, DeepSpeed is very popular. So we're using DeepSpeed as a framework, and we are using Theory 3. And 128 A100 GPUs are used, and the network bandwidth connecting GPU machines are 400 gigabit per second. And the remote storage bandwidth is 20 gigabit per second. And the model size evaluated in the paper is 100 billion. And we are considering 2 baselines. The first one is we call Strawman, which is the practical checkpoint frequency from the Blue, which is an open project, like in the academia, to train a large language model. It's we'll save checkpoints every 3 hours. And another one is high frequency. It's not a real solution from papers. It's just in theory, it is the highest checkpoint frequency we can achieve in theory, which we assume the checkpoint traffic can saturate the remote storage bandwidth capacity. It's the maximum. It's the best we can do with the remote storage system. But actually, people are not doing that. And because Gemini can save the model states for every iteration, we can say Gemini can, for the checkpoint frequency, Gemini is 170 times higher than the Strawman, and it's still 8 times higher than the high freq. And for the training efficiency, because Gemini can utilize the idle time span in the network, so it doesn't incur any. So theoretically, it doesn't incur any penalty on the training throughput. We also observe this performance. See, we measure the training throughput without any checkpoint, and Gemini with checkpointing transfer from GPU to CPU, also to other machines. The iteration time is very similar. So it means Gemini incurs negligible overhead on the training throughput. And we also do a validation study because let's look at the GPT-2 100B model. The iteration time, the idle time spans in the network in each iteration is around 10 seconds. It's very long, but Gemini can finish the checkpoint traffic less than 3 seconds. We still have a big buffer in the network for the idle time spans. In summary, the pre-training of large models can suffer from frequent failures because of thousands, even tens of thousands of machines get involved in extended training time, 4, 6, 8 months is also possible. So we propose Gemini, which the key idea is to save the model states to CPU memory instead of the remote storage for final recovery, and it can achieve the optimal checkpoint frequency. We can save the model states for every iteration, and based on our evaluation, the training throughput is almost the same as the baseline without any checkpoint. And because in our design, we don't assume any specific parallelism. So we believe this design is applicable to different parallelism strategies for training. I think this concludes my talk. I'm happy to take any questions from the audience.